So we're going to start chapter 9, and chapter 9 deals with, as you can see, the topic of chemical bonds. So let me go to full screen here and let's get started. So what do we mean by this term bond in chemistry? Well, a bond is basically a force of attraction that holds atoms together in molecules and also keep ions in place when it comes to ionic compounds, right? So without these forces, these molecules and ionic compounds would simply fall apart, all right? So that's what we mean by the term chemical bonds. So the key thing you need to remember about these bonds is that it doesn't matter if it's molecular compounds you're dealing with or ionic compounds, these are electrostatic forces, which means basically that these are forces that exist between positive and negative charges. And as stated here, the final or net force, which would be the bond, is basically the balance between the forces of attraction that is existing between these charged particles, all right? But the net attraction is basically what is responsible for the chemical bonds. All right, so just to give you an example, let's say we have two hydrogen atoms coming together to form a molecule. Well, in this case here, this molecule is short an electron, so therefore this is the H2 plus ion. And this is just basically showing you the forces at work. As you can see, it's a combination of attractive forces between unlike charges, between the protons and electrons here and here. And of course, we have repulsive forces. And basically, the extent to which this structure is held together is due to how strong the attractive forces are compared to the repulsive forces. If the net result is that the attractive forces are greater than the repulsive forces, then the structure will hold together, all right? So that is shown here in the case of H2 plus, and that is shown here in the case of H2. These are just basically all the repulsive forces between like charges here and here, and the attractive forces that exist between the positive and negative charges here, 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 and here, all right? So as stated here, what's the net effect? Because we know that we have attractive forces and repulsive forces, and what's the net effect is the question here, and the answer is that it depends on how close the nuclei are to each other. And that will be shown in the next slide. If you look at this graph right here, which shows you the plot of energy, and this is specific for the hydrogen molecule, right, where you have two hydrogen atoms bonded to each other. So the the y-axis here represents the energy. The x-axis here represents the distance between the two nuclei, or otherwise known as the internuclear distance. So therefore, you'll notice that, okay, the minimum part here, the minimum part of this curve, is basically where the molecule is most stable, and the internuclear distance in that case is 74 picometers, all right? But if you were to compress, let's say you could somehow force the atoms closer to each other, then what will happen is that the energy will rise, all right, as you can see here. And therefore the structure will become more and more unstable, all right? And that basically continues up to infinity, pretty much. On the other hand, if you're pulling the atoms apart from each other, then what you'll find initially is that the energy will rise because there's some resistance to your pulling the atoms away from the nuclei or from each other, because what is happening is that you're basically reducing or you're increasing the distance between the nuclei and the valence electrons. We're going to talk about the valence electrons and their role in this later on. And basically, there will be some resistance to that pulling away. So that's why we have the potential energy increasing until you get to a point where the distance between the two atoms are so far away that there's no more attractive force between the nuclei and the electrons of the other atom, and therefore basically the energy will just level off to zero, all right? So that's basically what happens in the case of hydrogen, and this is basically typically representative of what happens in any covalent bond, all right? Okay, so this is just showing you what happens as the atoms are getting closer to each other. You have increased attraction between the valence electrons and the nuclei from the separate atoms until you have the formation of the covalent bond here, all right? And therefore, this is very stable. And then as you try to separate them, the repulsion increases, and therefore the energy increases accordingly. All right? Okay, so now we're going to get into the actual theory that is used to explain the type of bonding that we see in molecules and ions. And this is called the Lewis theory, right? And the first assumption in this theory is that the valence electrons play a fundamental role in chemical bonding. Now, if you remember, we talked about valence electrons in the last chapter. The valence electrons are those electrons occupying the valence shell, which is the highest energy shell in the atom. Now, when you have a compound formed between a metal and a nonmetal, then usually what happens is that you have the transference of valence electrons from the metallic atoms to the nonmetallic atoms, and this gives rise to what we call ionic bonds, right? So the ionic bonds would be the attractive forces that exist between the ions after you have the transfer of electrons from the metal to the nonmetal. Now, in the case of two nonmetals coming together to form a compound, then instead of transferring electrons, what will happen instead is that you'll have the sharing of electrons between the atoms, all right? And as a result, you're going to end up with what is known as a covalent bond, or covalent bonds being formed between the two atoms. And we're going to say more about the covalent bonds later on, but basically what you're going to find is that in the case of covalent bonds, the forces would be as a result of the attraction between the shared electrons and the separate nuclei of the atoms involved in the formation of that bond, all right? And then this last statement here is saying that whenever you have the loss or gain or sharing of electrons to form chemical bonds, be they ionic or covalent, then the atoms tend to, but not in all cases, but they tend to end up with 8 electrons on their outer shell, all right? So we're going to see some examples of this shortly. But before we do that, let me introduce to you this concept known as Lewis symbols. And this is basically a very simple way of indicating the number of electrons on the outer shell of an atom. And it's very convenient for basically representing the structures of molecules. Later on, we're going to see how that occurs, and ions, and how these compounds are formed. So basically, all we do is that we write down the symbol of the element, and then we place dots around the symbol to represent the valence electrons, all right? Now, this here, I would not say that this is a hard and fast rule, because I've seen this rule actually being disobeyed in a lot of textbooks, but I'm going to go through it anyway. So it says here, in writing Lewis symbols, the first 4 dots are placed singly on each of the 4 sides of the chemical symbol, and then the dots are paired up as the next 4 are added, right? So for example, as you can see here, in the case of lithium, you have 1 dot here, and then beryllium, you have another dot placed here. Each dot represents a valence electron. In the case of boron, you have another dot here, and then in the case of carbon, you have a 4th dot here, right? Then, according to the rules here, you start pairing them up. So the next electron added to get nitrogen, you're going to place a dot pairing up with one of the dots that was there before, and then from nitrogen to oxygen, you have a pairing again, and then from oxygen to fluorine, there's a pairing here again, and then finally, from fluorine to neon, there's a pairing here, all right? So that's basically how we determine the Lewis dot structure, or the Lewis symbols for any particular atom. So basically what they're saying here in this last sentence is that when compounds are formed between these elements and other elements, and it doesn't matter if it's ionic or covalent, then what will happen is that they tend to end up with a group 8 element configuration. So for example, fluorine is a configuration that has 7 electrons on its outer shell. So therefore, when it reacts, it tends to gain 1 electron so that it ends up with the same electron configuration as neon, all right? Okay, so that's basically what Lewis symbols are all about. So if you're asked in this question, give the Lewis symbols for magnesium, silicon, and phosphorus, well, that's very easy. All you have to do is look for the group numbers and basically write down the symbols and place the number of dots around the symbol, which is equal to the group number. So in the case of magnesium, if you consult the periodic table, you'll see that magnesium is in group 2. So basically this would be the Lewis symbol for magnesium. In the case of silicon, which is in group 4, okay, what's going on here? 1, 2, 3, 4. And then in the case of phosphorus, which is in group 5, it's 1, 2, 3, 4, and then pairing up. And that would be the Lewis symbols for each of these elements. Okay, so we're going to stop this video here. And the next topic we'll be talking about is the formation of ionic bonds. All right? Okay, until next time.